Hello class, so today we're going to be learning about polymers. By now I trust that you have been given a handout sheet. So we're going to get started talking about what it means, what the word polymer means. So poly means many and mers means parts. And please keep in mind that all the information included in the handout will be included in your final exam. So make sure that you do answer all the questions in your workout sheet. Okay, so some of the concepts that we need to keep in mind is what a vinyl group is. So we're going to be working a lot with ethylene, and here you have your molecular structure of ethylene, and once you remove a hydrogen, it becomes a vinyl group. So this is really important to make polymers. As you have in your handout, you have two examples. One will be vinyl chloride, which is right here. Remember the vinyl, you're just removing one hydrogen. In this case, you're replacing the hydrogen with the chlorine. Then you also have vinyl alcohol. Over here you have your OH group, as you can notice. So vinyl chloride will be the monomer, and to make a polymer you will have polyvinyl chloride as your polymer. Vinyl alcohol instead makes the polymer polyvinyl alcohol. So we have covered in biomolecules how you can structure macromolecules out of monomers. So please refresh your memory on what each of the monomers are for the biomolecules. Now, again, we're going to be looking at ethylene, which is right here. So ethylene undergoes a process that connects the segments together to form a polymer, which is polyethylene. So this process is called polymerization, as you can notice here. And it usually takes thousands of monomers to make the polymer. So you have in your handout some boxes that you need to fill out with these names. So go ahead and do that. You can pause this video whenever you need to. It's okay. But I'm gonna get going because or else this video is gonna get very heavy for me to upload. You have a question in your handout that says identify the monomer from the reaction above. So of course it will be ethylene. This will be your monomer for polyethylene. And this just means that the chain continues, okay? So it continues. So when the polyethylene chain is finished growing, you add 2 hydrogen atoms to cap. So that means that the chain is finished. So you have one hydrogen should be added here, the other hydrogen right here. Okay, so now we're going to move on to a very interesting part. The architecture of polymers. So as you can notice, and we have already discussed this for biomolecules, structure is crucial for function. Okay, we already talked about that when we covered biomolecules. So for polymers, I just want us to focus on linear and branch. So obviously you can tell the difference between those two. In the linear, you just have one little worm right here. Over here for the branches, you have like a tree, you have many branches. So for the unbranched, which is the linear chains, okay, unbranched, meaning that there's no branches available, this will give a characteristic to the polymer, which means that they're usually referred to high density. So we're going to be talking again, going back to polyethylene, right? So right here, sorry, the ethylene is the monomer, polyethylene is the polymer. So whenever you have polyethylene and the linear structure, okay, this is a linear structure. it will be a high density polyethylene, and we refer to this as HDPE. So remember that when we were talking about cis and trans, when we were packing all of those molecules together, okay, one will be more fluid, the other one will be more rigid. So using those ideas that we covered for cis and trans, let's look at this linear. So imagine that you're packing together a whole bunch of linear structures, okay, of this polymer. So if you're packing all of them together, they can easily form a crystalline structure. So that will make it very strong and stiff, okay, very rigid, okay, rígido, right? So it will also make them very thinner, okay? So the products that are made of linear structures, which are high density polyethylene, HDPE, they can carry more weight. But it's not really good for sharp objects. And then we will look at examples and you will try to make the connection. It will all make sense, I promise you. So this is ideal for paper, tissues, and food, and it's more economical, okay? Now, let's look at the branch. You have many branches over here. And this is the same, we're working with polyethylene. So whenever you have a whole bunch of branches, that will give a low density. And then we will later on discuss the why it will give low density. So the more branches you have, that will be low density polyethylene, which we use the term LDPE. Okay, and over here you have two differences, like the linear is just one linear structure of molecules. You have this black sphere will be the carbon, the white one will be the hydrogen. Sorry. So, and then for the branch, you have a whole bunch of carbons and hydrogens sticking out. Okay. So for the one that's branch, meaning that it has low density, so we refer to it as LDPE. And as you can see in your handout, you will see LDPE, so that stands for low density polyethylene. HDPE stands for high density polyethylene. So for the low density polyethylene, they do not easily adapt. They cannot make crystalline structures because remember, when you're stacking all of these together, you're packing them, it has a whole bunch of branches. Instead of for the linear structure, it's very easy to pack them up together. For the branch, you can't. It's really hard. So it will not adopt any crystalline structure. So it will be softer and weaker. It will be thicker and more flexible, and it will hold less weight. So now we're talking about, you know, the products that are made out of branched polymers, or LDPE. It also has a high puncture resistance. So that means that it's high puncture. The puncture resistance is a measure of a maximum force over energy required to penetrate a material. So then we will talk about examples and it will all make sense to you. So over here you have some examples. So some of these examples are high density polyethylenes, and some of them are low density polyethylenes. So the branch polymer, which one was the branch polymer? Let's go back. So the branch polymer will be the LDPE. So the branch polymer molecules cannot pack together as closely as linear molecules can. So which one was the linear molecule? The high density polyethylene. So again, branch polymer molecules cannot pack together as closely as linear molecules can. So the forces holding these polymers together tend to be much weaker. So which one will be more weaker? The one that it has a lot of branches, the LDPE. This is the reason why the highly branched, low-density polyethylene is very flexible and is used for packaging film. So like this one right here. And plastic grocery bags. While on the other hand, the linear high-density polyethylene is tough enough to be shaped into objects such as bottles and toys. So now you can see the examples and you can see how the molecular structure influences the function. Now, we're going to be talking about two different types of polymers. One will be natural and the other one is synthetic. So for synthetic polymers, they're derived from petroleum oil, as described here, and they're made by scientists and engineers. Okay, so obviously synthetic is man-made. On the other hand, natural polymers occur in nature and can be extracted. So, and they're often water-based. So this is really important. Why is this really important? Remember when we were talking about biomolecules? I'm not going to mention the reaction, but you know what reaction you need to form the macromolecules and biomolecules. Remember? You need water or you remove water, right? So keep that in mind and remember the type of reaction that you need. And then lastly, in your handout, you have a table in which we're going to be comparing natural versus synthetic polymers. So you have a list of polymers, and then in another column you have natural or synthetic, so you just have to then identify whether if it's a natural polymer or a synthetic polymer. And then you're going to describe to me in your third column what monomers make that polymer. So obviously you have DNA, proteins, and cellulose, which will be our natural polymers. And by now you should already know what the monomer is for each one of those natural polymers. We talked about polyethylene, which will be a synthetic polymer, and you should know by now what the monomer is for polyethylene. Then you have nylon, which is right here. You have nylon, and these two will be the monomers. And of course, nylon is synthetic, it's man-made. And then you have Teflon, which is right here, and this is the monomer of Teflon, tetrafluoroethylene. And of course, it will be a synthetic polymer. So this is all that I have for you today. This is just an introduction, and throughout the week we will be discussing more in detail some examples of polymers. This is an announcement. So a core activity will be posted as an announcement. Please make sure that you read the instructions. And then tomorrow you will have an activity, and then the following day you will have another activity, which will be activity 2 for your third partial. And then we also have 2 sessions in which you will be working on your a lab report. Well, it's a laboratory component for the third partial that we need. Okay, so thank you so much for watching. Have a good day. Bye bye.